This video is part of a series aimed at people interested in using databases in their Unreal projects, or those who are maybe a bit curious about what it might offer them. This part is a basic introduction to relational databases, using game-focused examples with SQLite, but could easily be using any SQL-based database. If you already know your way around SQL and database schema design, this video is probably not for you. It is aimed at people fairly new to the subject. The goal is to help game devs get quickly started making their own databases, tailored to specific game requirements. So, relational databases. Relational databases in some form have been around pretty much as long as programming has, and sometimes learning about them has been mired in a lot of theoretical ideas and terminology that in all honesty haven't always translated well into real-world applications and practical usage. Doing things in a manner that works well and makes sense is obviously a good way of working, but ultimately getting results, in this case a finished game that works well and is bug-free, is our real goal. So if you feel that you prefer to do something in a different way than I advise, or use your database in a manner that the community at large does not agree with, as long as it works for you, stuff them. Go do it with my blessing. Anyway, let's crack on. Rather than give you a load of theoretical ideas, I'm just going to jump right in and work on creating a database that could be used for a game. If you follow along, you'll pick up the core concepts, and we will do a summary at the end to go over all the important points you need to understand. If you've already watched a previous video in this series, then you have an idea of the database we're going to make and how we will begin using it. The game is a kind of sci-fi RPG type of thing, but the same principles would apply to pretty much any genre. I'll start by giving our project a working title, something with wide audience appeal. I'm going to call it Alien Warmonger Universal Aggression.
I'm stoked. That title alone is, bound to attract everyone of all demographics, from hardcore Twitch gamers to the Stardew Valley crowd. So we're off to an excellent start. I just know it. This game will sell itself. I mean, I should, probably quit my real job and just concentrate on making this game, 24/7, right? I should, take out a loan or something.
Okay, let's first make a new SQLite database for this project. I'll use DB Browser for this, link in the description. New database, Alien Warmonger DB. So, relational databases store data in tables. When you define a table, what you are doing is giving it a name and specifying what fields it will have. Fields are the individual pieces of data that together make up a record in the table. So, the table has a name, and each field has a name. And with most relational database engines, each field also has a data type, which determines what sort of data will be stored in the field. If you're a C++ programmer, it's the same thing as declaring a variable. Each variable has a type of data that you're going to store in it. This is far more important in most other relational databases than it is in SQLite, because regardless of what you actually specify, SQLite will let you store whatever you want in each field. It's a SQLite thing, so just roll with it for now. When a player starts a new game, they go through the fairly familiar pre-game character creation process business. Their choices will set them up with certain traits and skills depending on what they choose. We decide the player will first choose a background, basically what the character spent the majority of their life doing. So let's make a table for those. It's going to be quite simple, and I'll call it background. Just 3 fields. Background ID, which is a number, integer, and is the primary key, or PK. A name, which is text, and a description, which is also text. So, you're wondering what that PK thing, primary key, I slipped in there. Primary key means the field, or sometimes several fields, that uniquely identify a single record in a table. It's like a phone's IMEI number, a citizen's national insurance number, a car's VIN, your passport number, that sort of thing. Only one record in that table can have a particular PK value. Here we're using integer, which is often the most usual, but you could use other things if you wanted to. Right, so let's put some sample data in there quickly. Nice. You might notice I didn't supply the background ID values when I entered those pieces of data. That's because if you have an integer PK field in SQLite, it will fill them in for you, giving each new record a unique value automatically, which is quite helpful. Later on, when we use SQL queries to insert new records, there's also a method we can use to find out the ID for a new record that we just created. Anyway, looking at what we just did might remind you of something. Kind of similar to enums in programming, right? I mean, in this case, it's fundamentally a number and a name attached to it, and we had the choice of specifying each ID number ourselves if we wanted to, or letting the system do it for us. Okay, we added a description too, but you can sort of do that with uMeta display name in C++. I will talk more about this point later on. So, that's the character's background. What about something a little more specific? Let's give the character some sort of job title. I'll call the table CharacterClass. This is the job or role that the player's character has. Probably it would decide their starting skills and equipment, that kind of thing. You've played games, you know the deal. It's going to be really simple. In fact, it's going to start out pretty much the same as the last table. Character class ID, which is a number, integer, a name, which is text, and a description, which is also text. Character class ID is the primary key. Chuck a few sample records in there for flavour. You might have noticed that I didn't fill in the description field. It was left nullable when we designed the table, and with databases in general, null is actually considered a value, albeit a null one, if you allow it. I wanted to show you how that worked, and not because I couldn't be bothered coming up with anything to type in there. So, when the player starts a new game, they get to choose their background and a character class to play as. But looking at those two things we just made, I feel like, well, maybe your choice of character class might be influenced by the background your character has. It's up to you, of course, but maybe in your game universe you decide there are not many advanced pastry chefs who learned their craft during a childhood on a penal colony planet, or for that matter, gene commandos who graduated from culinary school. But no problem, my friends, let's relate those tables to constrain which character classes are available with each background. We will start by adding a background ID to the character class table. We call this a foreign key, or FK. If a PK field from one table is used in another table, that's what it is, a foreign key field. Now, we want to actually create a formal relationship between those two tables. The relationship will stop us from adding data which doesn't make sense. In this case, we won't be able to have character class records that don't reference a valid background record. But unfortunately, we can't do that right now, because rather than make all these database structures first and then add the data, like we probably should have done, in our excitement we stuck a load of data in there right away. And now our character class table has null values for all the new background ID that we just created, which means if we tried to put our relationship in, it would fail. So what we need to do is change the data so that it is valid for the change we want to make, and then we can specify the relationship. There are cool ways we can do this really quickly and easily with a simple SQL query, but for the moment let's stick with what we already know and just manually edit a few values in DB Browser. It's sufficient to put any valid value in there for now. We'll go back and change them properly later, and in future we'll design everything perfectly before ever putting in any data, right? Right? Okay, data's all fixed up. Let's make the relationship. If you're one of those kinds of people who like to do everything with command lines and text, you can just specify the relationships in the SQL you use to create the table. DB Browser also lets us specify the relationships using drop-down lists, like this. This DB Browser example here shows us what the SQL to create the table, including the relationship, looks like. And you can create all your tables and relationships just by executing SQL scripts, if you prefer. And now we have the relationship sorted. I'll go back and change those background ID values to something more appropriate. Done. So, let's make another table. Continuing with the obviously pacifist theme of this game, WeaponType. Again, this is just going to be a simple table with an ID and a name. I'm not even going to bother with a description field for this one because, well, I'm lazy. Great, so now we have three tables which are a little more than enums, but in a database. We've already made a relationship between the player's background and the character class table. In the world of relational databases, there are very specific names for relationship types, but we will simply call this a one-to-many relationship. One background record can have many, or zero, or exactly one, related character class records. This is a parent-child type relationship, and it's very common. Consider country, county, village, solar system, planet, moon. Musical genre, band. We might say that the child records belong to the parent, which, depending on the nature of the data we're talking about, might be true. But remember, if we want to, we can change a child record's parent just by changing the foreign key value to point to a different parent record. The one-to-many kind of relationship is not good for all types of data though. In fact, one of the examples I just gave you might have a problem. What if there are bands that play more than one type of musical genre? Then the one-to-many relationship no longer fits the situation. So how can we deal with that? Well, what we are saying is that a band could potentially play many genres, but also a genre could potentially include many bands, and we call that situation a many-to-many relationship. Unfortunately, you can't make that kind of relationship in the way we did earlier. If the band table tried to have a foreign key to the genre table, and the genre table tried to have a foreign key to the band table, and they both enforced those relationships, then you would have an impossible situation. You wouldn't be able to create a record in one table without having the related record in the other, which you couldn't create because it needs the record in the first table, which you couldn't create. You get my point. Both the tables are effectively parents. Neither owns the data in the other. So instead, we make this kind of relationship by making a third table, which stores the relationship data between the other two. Honestly, it's not as bad as it sounds. The following example should make it a little clearer. We decide for our game that certain types of weapons can only be used by certain character classes. That's a potential many-to-many situation right there. Convenient that came up, right? So, let's clearly state what's going on. A character class can potentially use one or more weapon types. A weapon type can potentially be used by one or more character classes. Time to make the many-to-many table. I'm going to call it character class weapon types. Snappy. I'm going to give it character class ID and weapon type ID. I'm going to select both of those fields together and make them the PK, because the combination of the two things is what makes a unique record. It wouldn't make sense to let someone create it more than once. Now that's done, I'll set up the relationship definitions. Nice. Just a quick side note about naming things. Different people have different naming conventions, and each fight about them and make arguments why their way is better than someone else's. And generally speaking, I don't care too much about these things. But in case you're interested, when I name tables in my databases, I use the singular form of whatever name I want to give it, because otherwise every table in your database will have a pointless S on the end of the name, and they're tables. We know they can store multiple items. We don't need reminding with the name. However, when I make a table for a many-to-many relationship, I generally do pluralize the name, because then it indicates that's what it's for. I do what works for me, and as long as I don't have to read your code or work with your databases, you go right ahead and do what works for you. I mean, the database doesn't care. It all still works the same. So, we now have our many-to-many table, and it means we can create whatever character classes and weapon types we want, and then relate them to each other in the new table. As seen in the example in the previous video, this will all be used when the player starts a new game and goes through the character creation process. In that example, we pulled data from that database, using some SQL queries, which I also stored in the database. The code and the database is all on GitHub, so you can go right in there and see exactly what's what. But to make things easier, let's examine how those basic SQL queries work, so that you're better prepared to have a bash at making some of your own. The first query is used to retrieve the data for the different backgrounds the player could choose for their character. When we write SQL to retrieve data, the keyword we use is select. The way we use select is we specify all the fields we want to return and the name of the table to get them from, like this. SQL doesn't care if your query is on a single line or spaced out on multiple, like I have done here to make it nicer for humans to read. So, the first line says we want a bunch of fields. The second line says the name of the table we want those fields from, and the last line says sort the data using the background ID. In the second line, from, you might notice that as well as the name of the table, I added a B immediately afterwards. This is not required. It is just something I tend to do automatically after years of writing SQL. It's called an alias, and it just means we can refer to that table in the rest of the query as B instead of using its actual full name. In this case, it isn't really that useful because we only have a single table in our query, and as such, we don't actually have to give the table name with each field in the way I have done. To see what I mean, here is the same example in a more simplified form. SQL is smart enough to know which table each field belongs to until you write a query that has more than one table, and they have fields with the same names. So the next SQL query is very similar, but this time we need to tell SQLite to filter the data it will return based on the background ID the player has already selected. We do this by using an SQL parameter. SQLite supports several styles of including parameters in its SQL queries, but I have opted to use only one of those, the @ sign. Just be aware that my C++ code framework only supports that @ sign. So let's look at the second query. Okay, the first two lines are functionally similar to the previous query. We ask for a bunch of fields, and then we say which table we want those fields taken from. This particular query has no order by clause, which is optional in this case, meaning we'll get the rows of data in whatever order SQLite wants to provide it, and that means it might be in a different order each time we ask for it. Although this is generally not the case with SQLite, it often is with some of the client-server databases for various technical reasons. This is why when you write queries that you expect to return more than one row, it's usually a good idea to have an order by clause in there too, for consistency. Anyway, the other difference is the inclusion of a where clause. Where allows us to include filters in the query and has some simple yet very powerful abilities. In this instance, we are using the simplest type of filter, saying that we only want records where the background ID is the same as a value which we pass in at runtime using a parameter called @backgroundID. But we could do other things like where c.color_r is greater than 128, or combine filters together such as only return rows where the color is bright by saying where C color R is greater than 128 and C color G is greater than 128 and C color B is greater than 128. There are many useful techniques with SQL for retrieving data and ordering or grouping it in a way that can save us time as programmers later on. While I will be covering some more examples in this video and some other videos I'll make, I can't cover everything that SQL can do. For that, you need some good SQL references. I would suggest the following, links in the description. SQLite.org, the official SQLite docs. They're good for answering specific questions by searching for keywords. They won't hold your hand and they won't teach you stuff. You kind of have to know beforehand what you're looking for. SQLiteTutorial.net has some fairly good tutorials for using SQL queries to fetch, sort, and filter data, and it has examples of joining tables in queries, which is a powerful feature of relational databases. So, let's have a quick recap of what we've covered so far. Relational databases store data in tables. We give tables a name to identify them. Tables are made up of fields. Each field has a name and a type specifying what data it will store, which is more important in other RDBMS platforms than in SQLite. Each table should have a primary key, also called PK, which uniquely identifies a single row of data. This can be an automatically assigned number, an auto number, which SQLite does for us for any integer primary key, or it could be a text field containing data like license plate number, citizen identification, or passport number. Anything as long as each row of data has a unique value. When one table will be related to another table, the PK field is included in that other table. In this case, we call it a foreign key, or FK field. In some situations, we use a composite primary key. This is where the primary key is a combination of multiple fields. Again, it must be unique for each row of data. In this case, meaning the combination of field values is unique. Be careful using this. If the table will be related to many other tables in your database, it will mean you must include all the composite key fields as foreign keys in those other tables. This can cause your tables to have many more fields than they require. Sometimes it's cleaner to use table restrictions to enforce those rules and just have a single auto number primary key. Example later. Structured query language, SQL, is used to interact with our database. We can use different types of queries to do different things. Insert to add new records to the database, update to change existing data, delete to remove records, and select to fetch data. So, after that recap, let's take a look at another of our Alien Warmonger database queries. This time, we'll look at get weapon types for class ID. This select query is a useful example because while quite small, it demonstrates several of the things a select query can do. It has a distinct keyword, meaning that only unique rows will be returned, no duplicates. It returns table fields and also shows how you can return arbitrary data that isn't in a table, in this case a field called description with an empty string in it. It joins or relates multiple tables together, character weapon types and weapon types. It filters the data with a where clause, in this case using a parameter we specify at runtime. It sorts the resulting table by weapon type ID before then returning the data to us. Probably the bit which causes most issues for people is the relationship join part. Remember, back when we made the database, we created primary keys, and then in other tables we included those fields as foreign keys. We specified relationships on the foreign key table, which means that we couldn't enter bad data. Data in the foreign key table that didn't relate to a valid record in the primary key table. That's all fine and good. The thing which confuses some people though, is that those relationships only affect entering or editing data. They don't actually do anything as far as querying the database for data. It is true that some database utilities might take a peek at those relationships when you use their custom query designers and make similar joins for you in your query that you're making just to save you time. But just bear in mind that every select needs to specify how multiple tables are joined together. It's worth taking a moment to explain how this works, but there are some very good examples available on the external sites I linked in the description. Our from clause contains the name of the table or tables, or views, we want to pull data from, or views to help filter the data. In this case, we're specifying the character class weapon types and the weapon type tables. Each table added to that list needs to indicate how you want to join it with at least one other table in that list. We do that by specifying one of several join types. And yes, there are several available and it can seem a little overwhelming at first. But like with many things, you'll probably find that you use one or two things much more than others. In this case, inner join and left join are probably the most common. We use it in our query by specifying the table we want to join to and an on clause which states the field or fields in the tables that will be used in the join. So in our example, we're saying we want to consider data from the character class weapon types table and join that to the weapon types table. We're using a left join here, which simply means consider all the data in the left table, character class weapon types, and only data in the connected table where the joined fields are the same, which means in our case we're only interested in weapon types that have been used in the character class weapon types table. Remember, don't let all this stuff overwhelm you. As a game developer using relational databases in your project, you're free to use as much or as little of the various features as you feel comfortable with. It's perfectly okay to start out with just some basic tables for storing data and a few simple queries to get it back at runtime. Add nested joins and complex filters later after you feel more comfortable with them. So just to reiterate what I said at the start, we're not trying to be expert database engineers. We're game devs who realize that relational databases can be a powerful tool for us in our projects. We try to do what we can in terms of best practices, but we're not going to get our panties in a bunch about it. Keep your eyes on the prize, a finished, published game. In the very first video at the start of this series, I talked about some common recipes using relational databases in games. This was fairly high level, just to illustrate the point. I would love to hear your ideas in the comments of this video. How do you think databases could be used with games? Do you have specific situations which you would like to use a database for, but you're not entirely sure how to go about it? Let me know, and maybe I'll make a future video taking a look at the possible solutions to these issues. The next video in this series will go back to the SQLite framework I made and take a look at the class uSplitDBBase. It manages multiple SQLite DB files for you, providing a save game system while merging them with a main static database at runtime to give you a single database you can run queries against. It was designed with large RPG type games in mind, but there's nothing stopping you from using it in simpler scenarios.